Hello, class. Welcome back. Today is lecture 21, and we're just going to be looking at lots of examples of Fourier series. Last time we sort of did a bunch of background, and together with the lecture, we defined the Fourier series. So let me remind you of what that is. Together with the lecture problems. Okay, so last time, but not just in the video, I didn't do everything. Together with the lecture problems, so I made you do part of it. We showed the Fourier series of a function is, well, first you have to say on which interval. So from negative p to p. So the Fourier series of a function on negative p to p is this thing, this giant looking thing. So the idea was we're trying to write f of x as a sum of these linear combination of these functions that goes on forever. And then we figured out the coefficients in the last video and in the lecture problems. So all I'm doing here is repeating what we got. So that A0 or C0, I think we called it, the first coefficient next to 1 is just this integral times 1 over 2p. And then the other ones, the other coefficients looked like 1 over p integral negative p to p. So for the cosine one, you do f of x times cosine of n pi over p x dx. So that's your coefficient. Coefficient of what? Of each cosine term, n pi over p x. So these are like your coefficients that you figure out. And so we'll be calculating lots of these things. So we'll also be calculating this thing. And then there was the sine part. So that looks sort of the same except with sines. Actually, it looks exactly the same except with sines. So easy to remember if you just remember one of them. So these are the coefficients of each term and the sum that we'll be figuring out. And then the thing that each coefficient has been multiplied by. Oops, it should be sine, sorry. Okay, so in total, you get this thing. So just think about this for a second before we move on. The idea is you have your function, and it's sort of like power series. You're just writing your function in a different way. And like if you don't go to infinity on these sums, what you're doing is you're getting approximations of your function using powers, not powers anymore, but sines and cosines with different periods in them instead of powers of x like we do with power series. And it still somehow approximates the function, which is cool. And it's sort of better. It works better than power series, but we're not really going to talk about like when it works. We're just going to assume it works, but there are restraints as to like when this actually works, when it approximates a function, and how it does so. But let's just jump in and do some examples of calculating this thing for practice. And then we'll just sort of throw that kind of stuff in as we go. So let's calculate some examples. And what we'll notice is we'll see these are good for periodic functions. So functions that just keep repeating. and piecewise smooth functions, which you don't know what that means, but the intuitive idea is you can have lots of pieces of a function that jump around, stuff like that. And the smooth part means like not too pointy. So it has nice derivatives. So nothing like you don't want things like this, like sharp corners would be bad. But if it doesn't have that, then it's pretty good. And this works from negative p to p. And then we'll see something interesting happens, which is what you're doing is you're saying you have your function on negative p to p. This thing we have up here, this Fourier series, as you put more and more terms, it'll look more and more like the function, but then it'll also do some more interesting stuff after that. Okay, so power series just follows the function exactly, and that's about it around wherever you center it. But these Fourier series, they do something more afterwards too, which we'll find out. All right, but let's get to an example. Okay, so we're going to expand. So we need a function. It's going to be piecewise, just to show how this works nicely for piecewise functions, pi minus x. So I got to say when. So this will be between negative pi and 0. And this will be after 0 to pi. So expand this as a Fourier series. So let's just graph it first, just to see what we're dealing with here. So we're going from negative pi to pi. So that already tells us that our p is pi in that big formula above, which you should also think about as like the period of the function, because it's going to end up repeating itself after this amount. So anyway, that's p. What does this look like? So first it's 0. It's 0 from there to there. Not inclusive, so that's why I'm putting open circles there. And then after that, it's pi minus x. Pi minus x is a straight line with slope -1 that hits pi on the y-axis, so it's going to go up there. And then because the slope is -1, it just goes straight down like that to pi there. And technically that would be an open circle there. Okay, so this is what the function looks like. And now we're going to write down the Fourier series for it. And we know p is pi. Okay, so what we're just going to do is we're going to calculate each piece of the Fourier series. So first, let's do that integral up in the very first spot. So that's this one here. So now what is my f of x? Well, my f of x is a piecewise function. So what I have to do is I have to integrate each piece separately in order to be able to handle it. So what I'm going to do is I'm going to integrate from negative pi to 0. And remember, we can break up integrals like this. And then I'm going to integrate from 0 to pi, the next piece. And the reason for doing that is because that we get two different functions basically in these positions. So what is the integral, or what is the function from negative pi to 0? It's just the 0 function, right? That's what the piecewise function is defined as. It's 0 over there, so I'm just integrating 0 in that section. And then this 2 pi should be on everything. splitting it up like that. And then from 0 to pi, now it's using this other part, pi minus x. So the integral of 0, well, we don't have to worry too much about it because you can just think about it in terms of area. What's the area under this blue line here? It's just 0. So I'm not even going to think about it too much. That's just going to be 0. The integral of pi minus x is pi x minus x squared over 2 from 0 to pi. Now this part I'll do. So I plug in pi, I get pi times pi is pi squared minus pi squared over 2. Then you plug in 0, but that's just going to be 0 and 0. And so very quickly, this is pi squared over 2. So the pi's cancel and you get pi over 4. Okay, so that is the first coefficient. So now we have to do the cosines and the sines part, and then we'll stick it all together. Okay, so now we'll do the cosine part first. So it's 1 over p, but now p is pi, negative p to p. But these are both pi's now. F of x cosine of n pi over px. Okay, but p I said is pi, so we'll just change that there. And those pi's cancel, which is nice. Okay, so I'm figuring out these integrals all at once, where n is going to range from 1 to infinity eventually, but I'm just going to keep it as n now. And not just do each one separately. Okay, so same idea here. Because our function is piecewise, we are going to break it up into 2 pieces. So it's 0 from negative pi to 0. Oops, those pi's canceled, so now it's just nx here. And then, so I'll just distribute this 1 over pi this time to both. And then from 0 to pi, it's this pi minus x function instead. And same as before, this is just going to be 0 times something is 0. So then when you integrate 0, the area under 0 is just going to be 0. So we're not going to have to worry about that part at all. And just do this. Okay, so what's the integral of this thing? You can do integration by parts if you want, very quickly. So pi minus x and cosine of nx are my 2 functions. And I'm going to take derivatives on the left and integrals on the right. And I have this plus minus business, so I'm just using the table method to be quick. So the derivative of pi minus x is -1 and then 0. The integral of cosine nx is sine nx over n. And then the integral of that is negative cosine nx over n again, but now I have 2 of them, so I'll get over n squared. And then the integral is that times that plus that times that. So I end up with pi minus x times sine of nx. There's 3 negatives on the second term, so it's going to be negative minus cosine of nx from 0 to pi. Okay. So that is my integral. And let's continue. Okay, so now I plug in pi. So when I plug in pi, notice I get sine of pi minus pi is 0. So 0 times that, still 0, and then minus cosine of n pi. Okay, now I plug in 0, and I get pi minus 0 is pi, but then sine of 0 is going to be 0. So that's going to go away, and then cosine of 0 is 1. So altogether, I get 1 over pi times negative cosine of n pi and plus 1. think that's good. Oh wait, where was my division by n's? I had them and I didn't write them. Sine of nx had an n underneath it, and cosine had an n squared underneath it. So let's just bring those in here. So this is over n squared. And this is also over n squared. And this was over n, but that's going to be 0, so that's okay. Okay, so these were all over n squared. All right, so what are we going to do? We're going to simplify it a little bit. 1 minus, I'll leave that blank for a second, n squared pi. Now this is what is there, but we're going to notice one thing. What is cosine of a number times pi, a whole number? So this is like cosine of pi, cosine of 2 pi, cosine of 3 pi, and so on like that. Well, what are these things? They're just plus or minus ones. So cosine of pi is -1, then cosine of 2 pi is 1, and then cosine of 3 pi is -1, and this pattern is just going to repeat. So what I'm going to do is rewrite this as -1 to the power of n, and that will do the same thing. Because if I plug in 1, I get -1. And if I plug in 2, I get 1. If I plug in 3, I'm back to -1. So it's the same pattern. So this is a common trick to use in Fourier series. The other one that I didn't use, but I could have used earlier, is I didn't actually have to plug anything in here. Well, actually, we'll see it next time, so don't worry about it. Okay, so that's that. That is my sine, or sorry, that's my cosine part. And now let's do the sine part. So 1 over pi, integral from -pi to pi, f of x sine of n pi, the pi over, sorry, nx, the pi is canceled already, equals, okay, we do the same thing, break it up into this, so that's just going to be 0, and then go from 0 to pi, and that's going to be pi minus x on that part. I keep doing n pi instead of nx. Okay, so that's going to be 0. This guy is going to be this, and we can use integration by parts again. But I'm going to let you do that on your own if you want to, just for practice. If you do all the same stuff, you'll end up with 1 over n. But what's going to be a little bit different is, so the end result is going to be 1 over n. So that 1 over pi will also cancel. Okay. But what you might need to use is the following. So you might get another cosine of n pi equals -1 to the n. So you change it to that. That one probably won't come up this time. But what will probably come up this time is that if you have sine of n pi, then that's just going to always be 0 because you get sine of 1 pi, sine of 2 pi, sine of 3 pi. Those are all 0 forever. So this also comes up a lot. And it probably comes up in this integral when you finish doing integration by parts, plugging in pi, and that's why a bunch of stuff goes away and you just end up with 1 over n. Okay, but I want to get lots more examples done, so I'm going to skip over that work and let you do it if you like. Okay, so now what is our function? So how do we write it as a Fourier series? Well, long ago we got pi over 4 as our first term, and we got our cosine. So here was the integral of all that stuff, and we just did it. And what did we get? 1 minus -1 to the n over pi n squared, or n squared pi. And so those are just coefficients of each cosine, each multiple of cosine. So remember, this was a pi over p, but then p equals pi, so they canceled. And now our sine terms, if you just trust me that we got 1 over n, then our coefficients are just 1 over n. And then you have sine of nx. So this is our Fourier series for f of x that we had. And so what people do is they like to draw out just the first few terms. So what you can do is you say something like s sub 3 of x is the first 3 terms added together, meaning you plug in n equals 1, n equals 2, n equals 3, and you put them all in. So if we do that, let's just see what we get. So when I plug in 1 to the first guy, I get 1 minus negative 1 over pi cosine of x. And when I plug in n to the second one, I get 1 over 1 sine of x. So this is nx. Sorry, this is n equals 1 term. Let's go up to 3. So if I plug in 2 now, I'm going to get 1 minus 1 over pi times 4. But that's just going to be 0 already, so I'm not going to bother with writing the rest. And the sine term is going to be 1 over 2 sine of 2x. So this is the n equals 2 term. And then if I plug in 1 more, back to here. So this would be 9 pi cosine of 3x, right? Yes, plus 1/3 sine of 3x, and this would be third term. So this is just the first few terms as a function added together. But the nice part is that if you graph this, so this reduces a bit, by the way. So this is really just 2 over pi on that side. So, and this is just 2 over 9 pi. But if you graph this, you'll notice something cool. So I can't bring up the graph for you here, but what's going on is if this is negative pi and this is pi, then originally our function looks like this. Just like 2 straight lines like that. And our S3 will look something like, try to draw it as best I can. Something like that. And you can see it sort of looks like the function, but it's nice and smooth instead of jumping up. And this is what will happen with Fourier series. So this would be like S3 of x versus f of x. But as you write more terms, you'll get better and better looking things. So S4 of x would look even more like f of x. And so S5 would look even more, and so on like that. And eventually you start to see something that looks like a very squiggly line, and then it like jumps up and it's like very squiggly following along. It looks something like that. And it just gets better and better looking. And what's going to happen is it will eventually, as n goes to infinity, what happens is the Fourier series is exactly, it is the same thing, f of x, except on where it jumps. So right here, where it jumps, it's never going to be up here where it's supposed to be. Instead, it's going to always be in the middle of the two-sided limit. So like it's the middle of this brown dot and this brown dot here. So it'll always go through that spot there. But everywhere else it'll be exactly the same. Okay, so that's interesting and cool. All right, so let's do another one. Something else cool happens too that I didn't mention, which I'll bring into the next one. Okay, so let's find the Fourier series of just x. F of x equals x on negative p to p. So this time we're not going to choose p until after we're done. So what this allows you to do is create a more general formula. So notice I could have just done this whole problem earlier and kept these as negative p and p, and then I would have a formula that works for other numbers besides just pi. So it's better to do this. Okay, so we'll choose p at the end. And so this just is your classic straight line through the origin, slope 1. And it just looks like this. So we should get be able to get a Fourier series, and then the idea is that it'll sort of look like that. And as you graph more and more terms, it'll look more and more like this perfectly straight line. Okay. Let's do that. All right, so the first thing we need is that very first term. And here we're going to start to see lots of interesting tricks that we can use. Okay, so this one is just straightforward. Integrate x squared over 2. And then we'll notice that we'll just get 0 here because you get p squared over 2 minus negative p squared over 2, and the negatives go away. So you just get p squared minus p squared is 0. But we want to employ some new tricks. So you could calculate that, that's fine. So the other trick is that you could just quickly know it should be 0 because x, the thing you're integrating, is an odd function. So an odd function is one that is symmetric about the origin. And I just drew it before, but draw it again right here. And what does that mean? Why is that telling us that the integral is 0? Well, if it's symmetric about the origin, and you think about the area, the integral as area under the curve, signed area under the curve, then what's happening is the area under the left part will always match the area on the right part if it's an odd function. But their signs are different, so when you add them together, you'll get 0. And this will always happen for an odd function because it's symmetric about the origin. So another example is like x cubed, for example. We'll do the same thing. So this area will match this area, and they'll cancel to be 0 when you do the integral. So because it's an odd function, as soon as I know that I'm integrating an odd function on a symmetric thing for like from negative blank to blank, negative p to p, I'm gonna know I'm gonna get 0 automatically without calculating anything if I want. And this trick will come in handy with more complicated integrals that I don't want to do, and I just want them to be 0. Okay, so that part is 0. That's fine. So now let's do the cosine part. So now my function is x, so that's what's being multiplied to the cosine, and pi over px. So this time I'm keeping p the same, not changing it. And this will also be, luckily, 0 without having to do a bunch of work. And it's because x is odd and cosine of x is even. So together, this is odd. So how do I know this without drawing it? Because I said it's about symmetry. So the quicker way to think about even and odd functions is like this. An odd function, one which is symmetric about the origin, has the property that if I change all the x's to negative x, I end up with the negative of the function. And we can see that x has this property. So if I change x to negative x, I do get the negative of the function. So that's why it's odd. Meanwhile, even functions have the property that if I change x to negative x, the negatives just disappear, they vanish. And cosine has this property, which you'd have to prove a long time ago in trigonometry, but it happens. And this is also because it's symmetric across the y-axis, so it looks something like this. Symmetric. So then when I multiply an even and an odd together, what's going to happen is if I change all my x's to negative x's, the negative from the f will pop out and the g one will disappear. So this shows that f times g is odd because changing the negatives resulted in a negative popping out. Sorry, changing the x's to negative x's resulted in a negative popping out. So this is an odd function. So all that to say is, and you can test it right here, if I change x to negative x, I'll get the negative of this whole thing because the one on the cosine will disappear. And so this is odd. So I could just do that right here. Sorry, so I'm changing x to negative x. And I result in the negative of the original. So this is odd. And because it's an odd function, it's symmetric about the origin again. So the integral will be 0. If I integrate an odd function from negative p to p, because it's symmetric, I'll have this same property where the area down here and the area here will cancel. Okay, so a lot of work to explain why I don't have to do this integral, and I can just say it's 0. And maybe doing the integral would have been faster, but now I can just keep reusing this idea. So this part is all just 0. All right, so now we just need the sine part. So this one will not be 0. They're not all going to be 0, but instead, what's going on is this function is an even function, meaning if I change all the x's to negative x's, the negatives will cancel. And that's because sine and x are both odd functions. So if I change them both to negative x's, since sine is an odd function, that means I can take out its negative. And so that negative will cancel with the one on the outside, and I get back what I started. So this is the property of being an even function. plugging in a negative results in negatives disappearing. And when you integrate an even function, one that is symmetric about the y-axis, then the area on both sides will be the same. And so what you can just do is you can just integrate one side from 0 to p and then multiply it by 2. So whenever you integrate an even function, you can do this. So we're just going to integrate from 0 to p. We're just going to do half of it and then double the area. So we're going to multiply by 2. So it doesn't really save us that much time because we still have to do the integral, but you don't have to plug in negative p, I guess, at least. Okay, so that's because this is an even function. And now we got to do integration by parts. So the derivative of x is 1. Integral of sine is negative cosine divided by the number next to the x. So it's going to be times p over n pi. And then I have to do one more. Integral of negative cosine is negative sine. And I'm going to divide by the same thing. So I'm going to get p squared over n squared pi squared. Okay, so then the integral is equal to that times that plus that times that. So we get 2 over p times negative p over n pi x cosine of n pi over px. And then on the second one, the minuses will cancel, plus p squared over n squared pi squared sine of n pi over px. Okay, so that's my integral. And then I'm just doing it from 0 to p now. Okay, so we just plug in these things. All right, so we got 2 over p times, plug in p here. We are going to get negative p times x, and now p, so p squared over n pi cosine of p, x becomes p, so the p's cancel. I just get n pi plus, plug p to the second part, p squared over n pi, n squared pi squared, sine of, same thing happens here. The p and the b becomes pi, so the pi's cancel, and I just get, sorry, that x becomes p, so the p's cancel, and I get n pi. All right, so then minus, and I plug in 0. So I plug in 0. The first one, that x just makes everything be 0, and the second one, sine of 0 is 0, so that will go away. Nice and quick. All right, so let's simplify a bit. So I can take out a p squared, and that will cancel with the p on the bottom. I can take out an n pi if I want. And cosine of n pi is going to be there. And then here is going to be sine of n pi over n pi. And now we're going to use those things I said earlier. So sine of a number times pi, a whole number times pi, that's always just going to be 0. And cosine of a whole number times pi, that's always going to be negative 1 to the n. So we end up with 2 pi. We have this extra negative in the front, negative 1 to the n over n pi. This negative you can think of as another negative 1, so you could just make it be 2p times negative 1 to the n plus 1. That's fine too. Okay, so these are my coefficients. We are now done. So my function x as a Fourier series is, so the first thing we got was 0, the second, the cosine part we got was 0, but the sine part is here. And these are my coefficients. And now the things that they're next to are sine pi over px. Okay, so this is the Fourier series for x. And you could write out like the first four terms or something just for practice. So like S4 of x would be plugging in n equals 1, 2, 3, and 4. So let's do that. So 2p negative 1, that becomes squared, that becomes positive 1, over pi sine of n is 1, pi over px. And then now it'll be a negative 1 when you plug in 2. 2 pi over px. And then when you plug in 3, it'll go back to positive. And then when you plug in 4, it'll go back to negative. So now you see we could plug in p of our choice later at the end, so we can do this for various numbers. And so like if I plug in p equals 1, for example, then what's going to happen is that means I'm looking at this function from negative 1 to 1. And S4 is going to look something like this. But what I didn't mention last time, and what happens that's even cooler, is that it extends the function beyond just from negative 1 to 1. Meaning, so I got to think about it like this. This distance is 2. So if I go over to 3, what's going to happen is I'm going to get another copy of this. And it's going to go on like that forever in both directions. So there's going to be another one like this. So what this Fourier series does is it becomes the function on your negative p to p, but then it creates copies of the function over and over, so right and to the left. So it's much better than a power series, which just becomes the function near the center, but doesn't do anything else. So this is much cooler. Okay, so this is called I think it's called the extension, the Fourier extension of the function would be this red stuff. Okay, so one thing to just notice real quick is that this sort of thing will always happen if f of x is odd. I mean, we can make a bunch of stuff just be 0. If f of x is an odd function, this is something you want to check right at the start to save yourself some time. The cosine part will just be 0 again every time. And so we'll only get the first term and the sine part. So we'll just get this 1 over 2p integral negative p to p f of x dx. Although I guess this will always be 0 too. I didn't think about that, but f of x is odd on its own. So this will also be 0 every time. But you will not make the sine part be 0. So this part will not be 0. But what you can do is you can change the integral to 0 to p and double it instead. So your coefficients will simplify a little bit. And then this is called, because it only has sines in it, you can call this the Fourier sine series instead of just the Fourier series because it doesn't got any cosines in it. And so what we might expect is some sort of duality, meaning, well, okay, that's going to always happen every time if f of x is odd. And if f of x is even, maybe the opposite will happen. And that is exactly what works. So let's do that. So similarly, if f of x is an even function, the sine part will be 0. So what's an even function? An even function, like I said, is something that's symmetric about the y-axis, something like x squared. So it is symmetric about the x-axis. So you're just going to get the area under one side and double it because it's the same on both. And this will make the sine part go away, as we'll see. So let's see. Okay, let's do this. All right, but we'll show why it goes away. Okay, so, oh yeah, and then I also wanted to say the actual definition of even is if I change x to negative x, it disappears, and we see that it does. So that's another way to think of even functions besides using symmetry. Okay, so now we can continue. All right, so that first term is this. We can use our little trick, double it, and only integrate from 0 to p because it's an even function. Doesn't really save us much time here. All right, integral of x squared is x cubed over 3 from 0 to p. Plug in p cubed over 3p equals p squared over 3 yeah. Okay, so that's the first term, p squared over 3. The next terms, let's do the cosine term next. And what happens here? So again, I'll do my doubling thing. So I double it because this is an even function because their cosine and x squared are both even. So this will be an even function. If I plug in a negative x for x, all the negatives will disappear. And so because I'm integrating an even function, I can do this little trick here. Doesn't save us that much time, but that's okay. All right, so now I have to do integration by parts. I'm gonna have to do it twice. If you're doing it the long way, it'll take you a while. That's why I got this trusty old table here. So I just put the derivatives on the left of x squared, alternating signs. And on the right, I do integrals of cosine n pi over px. So the integral of cosine is sine. Gonna divide by n pi over p, which turns into multiplication by p over n pi. And then I got to do it again. Integral of cosine is negative sign, and now I'm going to have another of each of these. They're all going to be squared, and then I have to do it one more time. So I'm going to get cubed of each of these. Okay, so then the integral I'm looking for is that times that plus that times that plus that times that. And that's not so bad. All right, so I get x, I'll do this p over n pi x squared sine of n pi over px. Okay, the next line, the minuses cancel, plus p squared over n squared pi squared. I guess there's a 2 now, 2x cosine of n pi over px. And the last one, there is a negative, 2p cubed over n cubed pi cubed sine of n pi over px. Okay, and that's being integrated from 0 to p. Looks like a mess. Let's see. All right, change the x's to p's. That's all we got to do. So this becomes p cubed over n pi sine of n pi plus 2p cubed over n squared pi squared cosine of n pi. So we're very often going to get a bunch of stuff going to 0 and becoming -1 to the n. So that's nice. Okay, and then 2p cubed over n cubed pi cubed sine of, and then p over p is canceling, so you just get that. Then you plug in 0, you subtract. So that'll be 0 because of the x squared. The next one will be 0 because of the x. And the next one will be 0 because sine of 0 is 0. Okay, so that saves lots of time. That's the benefit of not having to plug in negative p instead. That's where the time is saved by using the even function property. All right, and now lots of stuff is going to go away. So sine of a multiple times pi, that's just going to be 0. We're using that property again. And cosine of a multiple is -1 to the n. So I just end up with 2p cubed over n squared pi squared times -1 to the n. Everything else is 0. And so I end up with 4p squared over n squared pi squared -1 to the n as my coefficients of cosine. Okay. Meanwhile, the sine one should go away like I predicted. So let's see. So why does this equal 0? It's because x squared is even. So when I change all the x's to -x, the negative that comes out of the sign has nothing to cancel with anymore. So I get a negative coming out, which shows that the whole thing is an odd function because x squared is even and sine is odd. And so I'm integrating an odd function over a symmetric amount. So the positive and negative areas will cancel to 0. So this is again showing the odd property. Okay. So then we're just about done. X squared equals, so that very first term was p squared over 3. The sine part is not going to be there, and I'm just going to have this cosine sum. So this is the Fourier series for x squared. And once again, what will happen is if once you choose a p, you'll get that your Fourier series looks exactly like your function there, but then it'll just repeat itself again over and over. So it's a periodic extension. That's what it's called. And so this one would be called a Fourier cosine series because the signs disappeared. So one thing you could do is you could just only look at cosine terms when you start with a function, or just only look at sine terms even though they don't necessarily go away, and create something called the Fourier cosine series or the Fourier sine series instead of the Fourier series. So next time we'll look at stuff you can do with those things. Okay, see you later.